A second commonly used form of line integrals is derived from the vector field notation used in the preceding section. If f is a vector field of the form f of xy equals mi plus nj, and c is given by r of t equals x of ti plus y of tj, then f dot dr is often written as mdx plus ndy. The line integral for f dot dr, then again, if f is equal to mi plus nj, and okay, and again, dr is found by taking r prime of t dt. So, and when you take the dot product of those, you end up with m times dx dt plus n times dy dt, all times dt. So when you distribute the dt's, they end up canceling out. So you have a line integral in the form of mdx plus ndy. We call that a line integral in differential form. This differential form can be extended to three variables, and the parentheses are often omitted. We have the line integral of mdx plus ndy, and we can also have the line integral for mdx plus ndy plus p dz. In this example, we want to evaluate the line integral that's in differential form, where c, the path, is given by the circle with a radius of 3. And by using the conversion equations, we know that x squared plus y squared equals 9 would be the equation of the circle. If you divide by 9, you get x squared over 9 plus y squared over 9 equals 1. And then you can find the conversion equation to get x equals r of t equals 3 cosine ti plus 3 sine tj. And the time interval is from 0 to 2 pi. We want to evaluate the line integral that's in differential form of y cubed dx plus the quantity x cubed plus 3xy squared dy. Now, because we know that x is equal to 3 cosine t and y is equal to 3 sine t, go ahead and find those differentials, dx and dy. You can find that dx, the derivative of x, is going to be negative 3 sine t dt, and dy is going to be the derivative of the y. It's going to be 3 cosine t dt. So that line integral can then be written, which began as this. We're going to replace each x in this line integral in differential form with what x equals on the path, and you're going to replace each y with what y equals on the path, and then you're going to replace dx with the differential x and dy with differential y. So it's really a bunch of substitutions. You do calculate those differentials, make the substitutions, and use the time interval for the path as your bounds of integration. You will end up with a single definite integral in terms of that single variable t. When you work this out, you end up with this. I would suggest using a graphing calculator to evaluate this and getting a decimal approximation. However, you can use some power reducing forms to rewrite this. Using the power reducing forms, you can go through and work this out to get the solution of 243 pi over 4. In this example, the line integral is in differential form. It's in the form of m dx plus n dy, but you don't quite see the n and dy. So that could mean several things. Perhaps the n is 0 or the dy is equal to 0. We can still solve this by making the substitutions. Try this one on your own and then come back and check your solution. All right, to evaluate this line integral in differential form, we do need to determine dx. dx would be that differential x. The derivative of 2t would be 2 dt. We can also find dy, however, in this case there is no dy, but if you practice it now, when you get to the others that will have dy's in it, you can make that substitution. The differential y is going to be the derivative of 10t which is 10 times dt. Now you're going to take this line integral, it's in differential form. The bounds are going to be the bounds for the path from 0 to 1. You're going to replace the x in the line integral with what x equals on the path. So that's going to be 2t plus 3. You're going to replace the y in the line integral with what the y equals on the path. So that's going to be 10t, that quantity squared, times your differential x, and differential x we calculated to be 2 dt. So now we have a single definite integral, single variable t. It can be simplified, and you can evaluate the definite integral to find the solution. When we simplify this, we get the integral from 0 to 1. That 2, we can bring that 2 out in front, and we get 2t plus 10t, that quantity squared is 100t squared, so that's going to be 300t squared dt. And you can evaluate that to get your solution, which is equal to 202. So that is an example of evaluating a line integral in differential form, making substitutions and finding those differentials, setting up the definite integral, and evaluating to solve.